Welcome to Ordinary Differential Equations, Lesson 29, the two-tank problem. The two-tank problem will involve a system of non-homogeneous equations. So let's just quickly review what we know about solving a system of non-homogeneous first-order linear equations using the method variation of parameters. The differential equation we want to solve is the derivative of y with respect to t equals a times y plus g of t. And we look for a solution of the form y of t equals the sum over all k, u sub k of t, f sub k of t, where the f sub k's were functions associated with the eigenvalues of the matrix, and also the eigenvectors or generalized eigenvectors as the case may be. And we had that u had to satisfy the following equation: u prime f1 plus u2 prime f2 plus all the way through un prime f sub n equals g of t. In other words, we can write this equation as capital U prime of t equals f of t inverse times g of t, because this stuff right here is basically u prime times f, and then we're multiplying both sides on the right by f of t inverse. So f is the matrix with the functions coming from the eigenvectors, the solutions corresponding to each eigenvector or generalized eigenvector. And u of t then we can find by integrating this integral of f of t inverse g of t dt. So here's the problem we have. At time t equals 0, let's think for a second down here, we have two tanks, tank A and tank B. Seawater flows into tank A, is mixed. There's an initial salt water in this tank. It might have a different concentration of salt than seawater. That mixture flows out into tank B, which is mixed, and then that mixture flows out, going somewhere. At time t equals 0, tank A has 1,000 liters of water mixed with 20,000 grams of salt. In other words, we have 20 grams of salt per liter. Tank B has 300 liters of water mixed with 10,000 grams of salt, so it has 33 1/3 grams of salt per liter. Salt water is pumped into tank A at the rate of 50 liters per minute. Seawater has 35 grams of salt per liter. The seawater is coming into tank A. The salt water in tank A is continuously mixed. The mixture in tank A flows into B and also at 50 liters per minute. Salt water in B is continuously mixed. This mixture flows out at 50 liters per minute. So the flow in here is 50 liters per minute. The flow out here is 50 liters per minute, and the flow out here is 50 liters per minute. So the volumes of water in these two tanks don't change as time goes on. So then we ask how much salt is in tank A at time t and how much is in tank B. So let's do the following. Let's let x sub A of t be the amount of salt measured in grams in tank A at time t, and similarly set up for tank B, x sub B of t. So the rate salt enters tank A is going to be 35 times 50 grams per minute. It's the concentration of salt in the seawater times the flow rate. Similarly, the rate salt leaves tank A is equal to the concentration of salt in tank A at time t, which is this thing times the flow rate 50. The rate salt enters tank B is the same thing because the rate that salt leaves tank A is also the rate that salt enters tank B. Same thing. And then the rate that salt leaves tank B is the concentration of salt in tank B times the flow rate. So then what we have is the rate of change of the amount of salt in tank A with respect to time is equal to the rate salt enters tank A minus the rate salt leaves tank A. The rate of change of salt in tank B is equal to the concentration of salt in tank A times the flow rate, salt enters here, minus the concentration of salt in tank B times the flow rate out right here. At time 0, we had some initial conditions. The amount of salt in tank A was 20,000 grams, and the amount of salt in tank B at time 0 was 10,000 grams. So let's change this to a matrix and vector equation. We just saw that we had this system of differential equations for x sub a of t and x sub b of t, the amount of salt in tanks A and B, and we had these initial conditions. So let's just rewrite these equations this way. The first one we can rewrite as the rate of change of salt in tank A with respect to time, dx sub A dt is this times x sub A plus 0 times x sub B plus 1750. Similarly, the rate that salt changes, the rate of change of salt in tank B is the rate that salt enters tank B from tank A minus the rate that salt leaves the tank B plus 0. 17,0, remember, was that non-homogeneous term that we had in our equation. The initial conditions are these. So then, looking at this, we have right here, we can put these two in a column vector. The derivative with respect to t of this vector equals, and now this stuff right here we can write as this matrix times this product plus one more vector here. So here we have a vector, here we have a matrix times a column vector, which is going to give us a column vector with 2 components, plus this other column vector with 2 components. The initial conditions can be written also in vector form. So what we have then is that the derivative with respect, looking at this equation up here, the derivative with respect to t of x, x sub a, x sub b, equals a times x plus b. A being this matrix, x being this vector, b being this vector. The initial conditions we can write this way. We might want to call them x sub 1 and x sub 2 instead of x sub a and x sub b. We will see maybe both of those as we go along. A little bit of inconsistency, I guess. So to solve a system of non-homogeneous ordinary differential equations, first order equations, we first solve the corresponding homogeneous problem, which is this one, without the g of t term added on here. So to solve this, we need to find the eigenvalues and eigenvectors of this matrix. And by a sage math calculation over here, we have variables defined, and then we're going to let I be the identity matrix, and A is going to be the matrix that we have right there, first row, second row. show A and show I, and we can see that it is this matrix and the identity matrix. Minus 50 over 1,000, for instance, reduced to lowest terms, fractionally, I guess, is minus 1/20th, and so forth. Then let's show the determinant of A minus alpha times I. What we're trying to do is to get the characteristic equation. I would like to use a lambda here instead of an alpha, but unfortunately in Sage Math and in Python, lambda has a different meaning. So we'll pick a different Greek letter. So the determinant of A minus alpha I, which I wrote here basically as lambda I instead, is given down here as 1/120th times 20 lambda plus 1 times the factor 6 lambda plus 1. And the characteristic equation is the determinant of A minus lambda I equals 0. And so this is what we have to solve. Well, that's easy to solve. Setting this first factor equal to 0, we get lambda is minus 1/20th. Setting the second factor equal to 0 gives us that lambda equals minus 1/6. So with a little bit of assist from Sage Math, we were able to solve at least this part of the problem pretty easily. We found the eigenvalues. Now let's find the eigenvectors of A. So first, let's find the eigenvector V of the matrix A corresponding to eigenvalue lambda equals minus 1/6. So we need to solve A times the eigenvector equals minus 1/6 times the eigenvector. We know that we can rewrite this equation as A plus 1/6 times the identity matrix times the eigenvector equals the 0 vector. And for this system of equations, here is the augmented matrix. The first two columns here give us A plus 1/6 I, and the augmentation is 0, 0. If you get the reduced row echelon form of that augmented matrix, it is this. The system of equations that you get from this is 7/60 V1 plus 0 V2 equals 0 from this first row, 1/20th V1 plus 0 V2 equals 0 corresponding to the second row. And so we see that in order for this to be true, first of all, for both of these equations to be satisfied, we have to let V1 equal 0, and then V2 can be any number. How about 1? So V1, V2 equals 0, 1 is an eigenvector for eigenvalue lambda equals minus 1/6. We could have picked V2 to be 2, for instance, and we'd have 0, 2. But that's just a multiple of this eigenvector, and it doesn't really count as an entirely separate eigenvector. It's not linearly independent from this one. So now we have found one eigenvector corresponding to lambda equals minus 1/6. What about the other eigenvalue? To find an eigenvector corresponding to lambda equals minus 1/20th, we'll do the same sorts of steps that we just performed. So we want A times that eigenvector is minus 1/20th times that eigenvector, and that tells us that A plus 1/20th times the identity matrix applied to that eigenvector multiplication here is 0, 0. The augmented matrix is this, and when we look at the reduced row echelon form of that matrix, we get what we see over here, which corresponds to these equations. And we see from this that if we let V1 be 7/3 and V2 be 1, that will be a solution to both of these equations. And so we can let the eigenvector have components 7/3 and 1. That is an eigenvector corresponding to eigenvalue lambda equals minus 1/20th. The same sort of calculation is shown over here. So we found two eigenvectors. This one, 0, 1, is an eigenvector for lambda equals minus 1/6, that eigenvalue. This is an eigenvector corresponding to eigenvalue minus 1/20. So the solution to the homogeneous problem, dx dt equals ax, can be written the following way. X sub a, x sub b equals an arbitrary constant c1, e to the minus 1/6 t times the eigenvector corresponding to this eigenvalue minus 1/6 plus c2, e to the minus 1/20 t times this other eigenvector, 7/3, 1. We will now use variation of parameters to solve the original problem. So here is the non-homogeneous problem that we're trying to solve. And if we get rid of this term, just make it 0, then we have a corresponding homogeneous system, x prime equals a times x, and we just found the solution to that homogeneous problem. Here it is. So in variation of parameters, we will substitute into this u1 of t for c1, u sub 2 of t for c2. We're going to replace those arbitrary constants with unknown functions of t. So x of t then will look like this, and we can write this as u1 times the vector function f1 plus u2 times the vector function f2, where f1 is e to the minus 1/6 t times this vector, f2 is e to the minus 1/20 t times this vector. So f1 and f2 are what I just mentioned that they were, and if you form the matrix F, which has as its columns f1 and f2, the matrix capital F is this matrix. Let's let u of t be the column vector with components u sub 1 of t, u sub 2 of t. u sub 1 and u sub 2 are scalar functions. In that case, we can say that x of t is u1 times capital F1 plus u2, times bold F1. Let's start that again. X of t is u1 F1 plus u2 F2, where F1 and F2 are column vectors, and we can rewrite that product here, sum of products, as the matrix capital U that we defined here times capital F of t, which is this matrix here. Capital F is formed by the columns the little f sub i's. Still going through our procedure for variation of parameters, we found the matrix F, and in Sage Math over here we can type in what F is. F is the matrix with these columns, and here it is. To compute F inverse then, we can do show F raised to the minus 1 power, and it gives us this matrix. So F inverse is this. U prime of t, remember, is f of t inverse, which we just found here, times g of t. And if we take this matrix f of t inverse and multiply it by g of t, which is a known column vector function, what we get is this matrix. So then this is the derivative of u. We can think of this column vector as u1 prime of t, u2 prime of t. So to find u1 and u2, we just integrate u prime. If you integrate this first one up here, you get this plus an arbitrary constant a1, the integral of 750 e to the 1/20th t is 15,000 e to the 1/20th t plus an arbitrary constant of integration a2. So u1, u2 then is this column vector. a1 and a2, remember, are arbitrary constants. So now we can write down the general solution to the ordinary differential equation, the system of ordinary differential equations. X of t is u1 times the column vector function f1 plus u2 times f2. u1 was this stuff, f1 was this, u2 was this, f2 was this. And then if you remember that x is the column vector x of a and x of t, this column vector is equal to all of this. And then if you look at the first component, x of a of t is this stuff times 0 plus this stuff times 7/3 e to the minus 1/20th t. That's what we get here. And it can be simplified to this. To find x of b of t, that's the second component of this column vector. Look at the second component of the column vector that we get by performing this computation. It's going to be this stuff times this exponential plus this stuff times this exponential, and that's what we have written down here. And then do some arithmetic and algebra, simplifying and simplifying again, and we finally get that x of b of t is 10,500 plus a1 e to the minus 1/6 t plus a2 e to the minus 1/20th t. So we found the general solution x of a, x of b to the non-homogeneous problem. However, we do have initial conditions given with our initial value problem, and those will allow us to find a sub 1 and a sub 2. So far, we've found that the general solution to the system of ordinary differential equations is given right here. Now let's remember that we had some initial conditions. How much salt was in tank A at time 0 and how much was in tank B at time 0. And those were 20,000 and 10,000. So substitute zeros in for the t's all the way through here. And we get from this equation that 35,000 plus 7/3 a2 has to be 20,000. And substituting 0 in for this one, we get a 10,500 plus a1 plus a2 equals 10,000. These are simple algebraic equations to solve a system of algebraic equations, linear equations. Solve them any way you like, and we find that a2 is minus 45,000 over 7, and a1 is 41,500 over 7. So now we can come back here and get the solution to our initial value problem. Substitute a1 and a2 into these two equations up here, and what we finally get is x of a of b is equal to this stuff just by substitution. And then doing a little bit of arithmetic simplification, we get that x sub a of t is 35,000 minus 15,000 e raised to the minus 1/20th t. And similarly, x sub b of t is going to equal this stuff, which isn't very nice looking, but that's what it is. So we have found x sub a of t and x sub b of t, the amount of salt in tank A and in tank B. It would also be nice to consider the concentrations of salt in those tanks, measured in grams per liter. How do they change with time? We know in general that the concentration of salt in a tank is just the amount of salt in the tank divided by the amount of liquid in the tank, water in this case. So C sub A of t is x sub A of t divided by 1,000. Similarly, the concentration of salt in tank B at time t is the amount of salt in grams in tank B at time t divided by the 300 liters of fluid that are in that tank. We can calculate what happens at time 0. At time 0, tank A had 20,000 grams of salt in 1,000 liters of water, so that gives us 20 grams per liter concentration. Similarly, for tank B at time 0, we had 10,000 grams of salt in the tank at time 0, divided by the 300 liters of liquid that were there, which gives us 33 1/3 grams per liter. And the seawater salt is unaffected as time goes on. It's always 35 grams per liter. So how should the concentrations change with time? Well, let's think about tank A first. Seawater is going to flow into tank A, and it has 35 grams per liter salt in the seawater. And in tank A, initially, there are 20 grams per liter of salt in that tank. So as time goes on, since the salt concentration in the seawater is higher than what it is in tank A, you're going to see the concentration in tank A go upward. And as time goes on, it should level off, I would think, at about 35 grams per liter. What about tank B? Well, if we look at what's happening here, tank A starts at time 0 with 20 grams per liter of salt. Tank B starts with 33 1/3 grams per liter of salt. So if you let this salt mixture flow into tank B, what's going to happen? The concentration in tank B is going to go down. The salt concentration will go down because you're flowing water, salt water, into tank B that has a lower concentration of salt than tank B had initially. But as time goes on, the seawater flowing through the whole system is going to wipe, I guess, what happens at short times out. It's not going to be, the situation's not transient. In both tanks, as time goes on, I think we would expect that the concentrations would approach 35 grams per liter. So let's take a look at the graphs and see what they look like. So here are the graphs, and here is some Python code, which can also be SageMath code in this case. You could put this just in a cell in a Jupyter notebook. We're going to declare t to be a variable, and then we're going to plot a graph in red for C sub A of t. We're going to plot another graph in blue for C sub B of t. And what we have then is just plotting the concentration of salt in the tank at time t divided by how much fluid is in the tank at time t. And for the second plot, similar, the amount of salt in tank B divided by the number of liters of fluid in tank B. And we're plotting these where time goes from 0 to 80. So if we look at this, for tank A, we start with 20 grams per liter of salt, and as time goes on, the concentration increases towards 35. 35 is up here, I guess. In tank B, we see that initially the concentration goes down because the salt water from tank A doesn't have as high concentration as tank B, but then eventually the concentration of salt in tank B also approaches 35 grams per liter as time goes to infinity. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.